Alright, good morning everybody. Welcome. This is Advanced Electrical Networks, lecture 4. A quick recap of what we were doing the last time around. We saw that if you had a network with only bilateral elements, namely things like resistors, inductors and capacitors, where you can relate either the instantaneous voltage and the instantaneous current by resistance or the voltage phasor with the current phasor by an impedance, then you can within course interchange the location of the excitation and the response as illustrated in this picture. And we saw last time that you can use Telegun's theorem to show that V2 by I1 is the same as V1 hat by I2 hat in the network on the right. Now, so apart from the mathematical curiosity of this and its elegance, it's got a very practical application, and that application is the following. Many times, particularly you will appreciate this when we start doing noise calculations. Many times it turns out that you are interested in transfer functions from multiple inputs to the same output. Okay. Now, the simple minded way of solving such a problem would be the first instinct, as many of you pointed out in the last class, would be to use network analysis to find the transfer functions from one source to the output one at a time using superposition. Correct? It turns out, as we again discussed in the last class, that there is a cleverer way of doing this if you exploit the fact that the network only consists of elements where you can relate the branch currents to the branch voltages in this fashion. And that is the following. So, you excite the output port, right, and then look at the voltages or currents through the independent sources inside the network, and this way you solve the network only once, but in one shot we are able to get all the transfer functions that we want without having to evaluate the network multiple times. Okay. Now, that is one of the advantages of or one of the practical uses of reciprocity. Well, there is still an issue, and that is that while this is great, most practical networks that we deal with as analog circuit designers are networks that consist of control sources, right? Voltage control voltage sources, voltage control current sources, CCVS and VCCS, and clearly there every branch voltage cannot be expressed as a linear function of its branch current, because the branch voltage could be dependent on the voltage across some other branch if it is a voltage controlled voltage source and so on, right. So, this is a great seemingly useful idea. Unfortunately, its applicability seems to be limited in practice simply because we do not deal all the time with networks where every branch voltage is related to its branch current. So, one way around it, as we saw last time, was to recognize that the problem with reciprocity, as we saw it, occurred only as far as the so this is I1, this is V2, and this is the network N, and as far as the branches where you have I believe we call these A and A prime and B and B prime. This is VB prime and this is IB prime, this is VA and VB. This is IB, which happens to be GM times VA. okay, this is Rk or Zk, whatever. So when we did the try to relate the port currents of when we wrote Telegon's theorem, we found that, oh well, it all works out except for the contribution of this control source, and we said, oh well, we found within quotes a hack, right? We said, oh well, it seems pretty straightforward to fix that problem, and that is, well, we just move the control source this way. So this is VB hat, and this current IA hat is, what did we see last time? GM times VB hat, right? If we did this, then all the terms other than the port voltages and port currents, when you write Telegon's theorem, just simply cancel out, and we see that, like with a network with bilateral elements only, we again have V2 by I1 is V1 hat by I2 hat, right. So, this network, as you can see, can you comment on whether this network and this network are the same? Are N and N hat the same? They are not the same, because we have taken that control source and flipped the controlled and the controlling ports, right. That seems intuitively reasonable, because in this in the network N, signal flows like this, right, and we have some transfer from V2 to I1, and if you want the same transfer from I2 hat to V1 hat, it seems reasonable that the control source points the other way, right. So, I am going to just write down. So, please note that N hat and N are not the same. However, given N, what comment can you make about N hat? I mean, is it like rocket science to find N hat or what? It is just a matter of flipping the controlled and controlling ports in the in N to arrive at Is that clear, people? All right. Now, if there were multiple voltage controlled current sources, what comment can you make about what are you going to do to derive N hat? Very good. So, if you have multiple voltage controlled current sources, what you want to do is simply flip the orientation of all the voltage controlled current sources to derive this N hat. And another aspect that I would like to point out is that if GM is set to 0, right, whether you have N or whether you have N hat, please note that the port impedances at between A prime and B prime remain the same. Is that clear? So, if you set GM to 0, what comment can we make about the impedance between A and A prime? It is an open circuit, and likewise between B and B prime, it is also an open circuit. What comment can we make about n hat if we set Gm to 0? It is the same. Is that clear? Very nice. So, therefore, in N, if we had a voltage controlled current source, so this is A, this is A prime, this is B prime, this is Gm BA, then in n hat we have A prime, B prime, B prime, this is Gm BB. All right. Okay. Now, this is a voltage controlled current source. So, I am not going to here we did the derivation and found this. You can do the same derivation for the other controlled sources. I will give that as a part of the homework, so that you are convinced, but I am going to only put down the final result here. Let us use our intuition to figure out what we are going to do. Let us if the original network had a voltage controlled voltage source, so this is VA, this is mu times VA. What comment can we make about what we need to do in n hat? This is A, this is A prime, this is B, this is B prime. I mean, we can derive it, but which I will leave for the homework. But what should you intuitively expect based on our experience so far? Very good. So, remember, the controlled and the controlling ports must be interchanged. So, B prime must be the controlling port, and remember, another aspect is that if mu is 0, you want the port impedances to all be the same. So, if mu is 0 between B and B prime in N, what comment can we make about the impedance we have? It is a short circuit. So, this must be the controlling port and must be a short circuit, all right, and so this must be a current controlled source, right, and what must be there between A and A prime in n hat? Well, its impedance must be infinite when mu is 0. So, therefore, this must be a current controlled current source. So, if this is IB hat, this must be mu times IB. All right. A common cause for confusion is the direction of the current. And what can we say about the direction of the current? What's a good way of remembering what the direction is? Remember, in the original network, if you yank VA up, so if VA increases, right, what tends to happen to VB? VB will increase, assuming mu is positive. Now, we turn the source the other way, and so if VB increases, right, VA must also tend to increase. So, if VB increases, IB, that IB hat will tend to flow in that direction we have shown. For that direction, we must expect the voltage between A and A prime to increase. And how will voltage across A and A prime increase? When you push current into A, correct? So, that is an easy way of remembering what direction you need to put the current source. Is that clear? Okay. So, now without further ado, let us write up the other cases. So, one is in fact, there is only one other case. What is that other case? Current controlled voltage source, because the current controlled current source is is the same as the voltage controlled voltage source, right. If you have a voltage controlled voltage source, we replace it with a current controlled current source in the opposite with controlled and controlling ports flipped. Likewise, if you had a current controlled current source, you would replace it with a voltage controlled voltage source with the controlling and the controlled ports flipped. If you have a current controlled current source, so this is IA, this is mu times IA, this is B and B prime. What should we do? This is A prime, sorry, this is a current controlled voltage source. So, this is say Z times IA, this is B, this is B at, okay. Let us see what we should do. Any thoughts? So, which is the controlled port and which is the controlling port? B is the controlling port, and what comment can we make about what kind of controlling port? Is the voltage across B controlling? It's a current controlled port. So, this is IB hat, and what comment can we make about the controlled port? It must be a voltage source. This is Z times IB. All right. Okay. So therefore, in summary, if you have an arbitrary linear network now, because the three RLC passive elements plus all the 4 control sources, right. With these 4, you can form any linear network that you want, correct. Now, if you are interested in finding the transfer functions from multiple inputs inside the linear network to a single output, right, you do not need to despair. All that you need to do is what is the to find the transfer function from multiple inputs in N to a single output. What should you do? What is the first step? Derive N hat from N, correct. And how do you derive N hat from N? Well, you simply look at this table, right. All the bilateral elements, namely the R, L and C, remain the same, and all you need to do is flip the control sources as per this table, right, which you know how to derive, okay, and therefore you have N hat. Then what do you do? So, excite the output of which port, of which network? Excite the output of N hat, right, with the appropriate current or voltage excitation that the situation warrants, and right, measure current or voltage, right, through or across the independent source. Does it make sense? Yeah. So, you know, as he points out, I mean, you know, it doesn't make sense to keep calling n hat, right? So, it sufficiently seems to be sufficiently nifty and important to have a name, right? So, n hat, I mean, you can see that the ports in n and n hat are reciprocal, except that n hat is not the same as n, but can be derived from n. So, n and n hat are called inter-reciprocal networks. Okay, and this is called inter-reciprocity.